Today we are going to go over the Hund's rules. Hund's rules. So Hund's rules determines in which way we are going to fill electrons on the electronic orbits of the atom. So, and Hund's rules apply to find the ground state of the atom. We have two rules here in the Hund's rules. First rule is for spin-spin coupling. When we have electrons adding to the electronic orbits, they need to have maximum total spin. So this corresponds to the electrons minimizing Coulomb interactions this way, because we know spin parallel electrons have minimum energy in this case. And second rule applies to the orbit-orbit coupling. In this case, we have to have for electrons total orbital momentum L, also having maximum value. This corresponds to the electrons minimizing interaction when they orbit in the same direction. And finally, third rule here applies to the spin-orbit coupling. In this case, we have to have shell. That's if it's shell half filled. In this case, we have total momenta equal to L minus S taken with the absolute value. And if its orbit is more than half filled, in this case we have J equal to L plus S. And third case, when we have shell half filled, we have J equal to S. So let's go to the next slide here. So in this case, we have a slide which corresponds to the 15 configurations of the carbon atom. So carbon atom has formula here: one S2, 2S2, 2P2. So we have two S electrons on the first orbital, and we have 4 electrons on the second orbital, n equal to 2 orbital, where we have 2 S electrons and 2 P electrons. Now, if you look here, in this case, we have here this carbon atom here, and here in carbon atom we have L equal to 1, because P corresponds to the orbital value of L equal to 1. L equal to 1 we can divide to 3 here levels having value of from -1, 0, and 1. And we have, I put here this table. This table shows values of ML values, which correspond to the values of orbitals adding of these 2 electrons here on the orbital, on the p orbital, and the values of the spin moment here. So we have here L1 equal to 1, L2 equal to 1, and finally we have L value equal to 2, and this corresponds to ML values, this quantum values of L equal to -1, -1, -2, -1, 0, 1, and 2. And for S values, we have here S equal to 1, which corresponds to have quantum values having MS equal to 1, 0, and -1. Now we have here, I put here the values, the configurations here. So for this configuration, when we have MS equal to 0, these 2 electrons have to have opposite values of spins, and we can put here on the L equal to 1, in this case L equal to 2 minus 2. So some other case of this case corresponding to this case, we have L equal to 2, ML equal to 2, and these 2 electrons we have to put on this orbital L equal to 1. Both of them will give us L1 equal to L1 plus L2 equal to 2. So ML corresponds to equal value of 2. Now there are 3 cases here. These 3 cases will correspond to L equal to 1, and these values of quantum numbers of L equals to -1, 0, and 1. So we can put these values of spins only parallel to each other, because we have here MS value equal to 1, and these three cases correspond to the parallel orientations of the spins. Now we have here as ms equal to -1, they will be just these states, but the directions of the spins directed downwards. So this will correspond to the ms equal to -1. Now here for the case when we have ml equal to -1 and ms equal to 0, we have to have two electrons with spins antiparallel to each other. So in this case ms equal to 0, but L equal to -1 will correspond to these configurations here. So this configuration gives us ml equal to -1. Now, parallel to that, we can consider here ml equal to 1 case, and this corresponds to spins when we put here at L equal to 0 and L equal to 1. Whereas we can put them at L equal to -1 and L equal to 0 here. So we can invert these directions of the spins, and we have second configuration, which is here. Now, for the case of ml equal to 0 and ms equal to 0, we have this orientation here. So all three cases will correspond to ml equal to 0, because here we have here -1 and here 1, so 0, this 0, 2, this ml equal to 0, because both values of L for these electrons L equal to 0. And all of these spins have to be antiparallel to each other, and they give us ms equal to 0. So if we count here, this here we have three states corresponding to the ml equal to 0 and ms equal to 0 case, and here we have 2, here we have 2, and here we have 1, and here we have 1. And to simplify these configurations, we can put them here in this graph. So. So we have here all this table here that I put here just number of configurations here. So last case that we had ml equal to 0 and ms equal to 0, we had three configurations here. And here one configurations, and here one, just by one configuration here. And here we have two configurations, and here two configurations. So altogether we have 15 configurations here for this case. But these configurations do not count to the Hund's rule. So Hund's rule only finds only ground state here. So now we can put here the term symbol for the atom here. So we have here now some number of electrons orbiting on external orbits, but instead of writing this formula here, 1s2, 2s2, 2p2, we can just use here term symbol here. So here we have s, this s value corresponds to the value of spin, total spin of these two electrons here, or some number of spins. And here j is just equal to the value of s and l. So we have two j values of the several j values of j according to the equation here that we have, for example, j1 equal to s l minus s, and all the way to the l plus s. So these values of s correspond to this. Now l, this corresponds to the abbreviation of the orbitals that we use, for example, for the case for single electrons. So s equal to 0. If we have L equal to 0, then in this case S equal to 0. S, we have S abbreviation, so instead of L, we have S here. And if we have here this P, we will have PL equal to 1. In this case, we have abbreviation P here. Now let us look at these cases when we had considered here. So one state has orbital moment of L equal to 2 and S equal to 0. So this corresponds to this case and this case, right? ML equal to 2 and S equal to 0. No, so s equal to 0, and we have 2s plus 1. Here, this index equal to 1, and this index equal to 2, only value of 2, because we have here l plus. Which one? Huh?
10 болды деп атырмын ғой.
Вот 5 тағы 5 бүтін не olur? Тұра берсең енді ұстап тұрып бермесең енді ақырына дейін 5 бүтін алсың. So we have here this 1d2 abbreviation for this case, because we have here d s plus l plus s. This corresponds to l equal to 2, and this corresponds to the notation of d here. Now three states have here orbital moment of l equal to 1 and s equal to 1. These are here, this, and this one. And we have here this s equal to 1, so this index will be 2s1 plus 1 equal to 3, all three cases equal to 3. And here we have l plus s again equal to 2. This corresponds to the notation of p. And the value of j here is equal to, starts from l minus s, 1 minus 1, 0, and l plus s, which is 1 plus 1 equal to 2. So we have 0, 1, 2, 3 there states here. So one state has orbital moment of l equal to 0 and s equal to 0, and this case corresponds to 1s 0 case here. Now we have different atoms here. For example, some atoms are heavy, some atoms are light. In the case of light atoms, we will have Russell-Sanders coupling. So Russell-Sanders coupling corresponds to the case when we have electron-electron interaction much larger than spin orbital interaction. So this corresponds to Russell-Sanders coupling, and this will be valid only for light atoms here. Now for light, if we consider this case, the notation will be just notation that we considered in the previous case. So we will have here the case of electrons that they will be independently that they will have independent values of momentum here. So this is notation for that case here, that we just considered. Now JJ coupling happens when we have electron interaction much smaller than spin orbital interaction. In this case, electrons will have the total momenta that will be equal to their spin and orbital momenta, and they will be and now we have to just to find out total momenta of the atom. We just need to sum all these momenta of electrons. So in this case, we'll have this notation. We don't have this notation, and we have only, we will count here j values. So for example, in this case j equal to 0, because we have here this value of second atom total momenta equal to 1/2, and here total momenta of first electron is 1/2. So 1/2 and 1/2, they will give us j equal to 0 here. Now here we have these energies, and these energies correspond to the light atoms and all the way to the heavy atoms. So for the light atoms, we have here as in the case of carbon, we find out these three states correspond to the ground state, and they correspond to the ground state because they give us smallest energy in this case. And these configurations just give us some the larger values of the energies here.